To execute any automated software test, the underlying system architecture requires a specific starting state. Before a single interaction can occur, the test engine must instantiate browser sessions, open database connections, authenticate user profiles, and initialize session logging. These are heavy, system-level prerequisites. But if this necessary backend setup code is injected directly into business-facing test steps, it directly violates the design rules of behavior-driven development. Look at this feature file. It is intended to be a human-readable definition of software behavior. When technical setup routines bleed into these files, the business logic is entirely obscured. As a test suite scales to hundreds or thousands of scenarios, this code pollution compounds. Product managers and business analysts can no longer decipher the test files to verify requirements, and test engineers are left maintaining redundant, fragmented setup logic scattered across every single script. An enterprise-grade automation architecture requires a hard boundary. The physical system prerequisites must be entirely decoupled from the behavioral business logic. The Cucumber framework provides a specific architectural solution to enforce this boundary: hooks. These are predefined annotations that intercept the execution pipeline at specific moments in the testing sequence. By utilizing hooks, the complex burden of environment setup and system teardown moves behind the scenes. The heavy lifting is separated from the feature file, restoring the test script to plain, readable text. This creates a hidden implementation layer. The logic embedded within these hooks runs autonomously in the backend. They do not require a user to explicitly call them or trigger them from the feature file. To build a stable framework, we need to map the exact chronology of how these autonomous intercepts operate. We will trace the complete Cucumber execution lifecycle, working from the outermost boundary down to the micro level. Controlling this invisible execution lifecycle is the primary method software development engineers and test use to maintain a dynamic, predictable grip on test environment states. The baseline structural unit is the scenario, representing a single independent test case. To prepare the environment, we introduce the @before hook. Triggered prior to the scenario initiating, this is where you launch the Selenium WebDriver or establish API endpoints. On the opposite side, we apply the @after hook as a protective boundary. Once the scenario completes its final assertion, this logic executes to ensure the browser is closed and session logs are flushed. The defining characteristic of the @after hook is its fail-safe nature. If a test passes perfectly, the hook triggers. If the test crashes midway through due to a critical application error, the engine immediately jumps to the after hook and triggers it anyway. By combining these two intercepts, we construct a non-negotiable protective wrapper. The environment is guaranteed to be clean at the start and safely dismantled at the end, regardless of the test outcome. We can zoom in past that global wrapper to investigate its internal structure. A scenario is not a single action, it is a sequence of distinct steps. To manage transitions, Cucumber provides granular annotations, the @before step and after step hooks. Tracking execution, the engine hits the @before step hook prior to step 1. It then completes step 1 and instantly triggers the after step teardown. This creates a rapid execution loop: prepare, execute, conclude. It repeats this micro loop for step 2 and step 3. Once complete, the execution path strikes the global after boundary to terminate the entire test. In practice, this extreme granularity is vital for forensic failure analysis. If a web element cannot be found on step 2, the @after step hook captures a dynamic screenshot of the browser at that exact second. Similarly, advanced logging frameworks use step hooks to attach specific JSON request and response payloads to the test report immediately after an API interaction occurs. This nested execution pipeline gives developers absolute control over the state of the environment during every single micro-transition of the automation run. But executing a global setup sequence before every single test creates massive inefficiencies. A test suite might contain tests that require a full browser layout, alongside backend tests that only require an HTTP client. Look at this comparison. Initializing a UI test is like starting heavy industrial machinery. It consumes high memory and CPU to launch browser binaries. An API test, by contrast, is like a data laser, frictionless. Running heavy browser code before a lightweight API test wastes immense computing power. To prevent unnecessary system setups, we use tagged hooks. We can bind our setup logic to specific scenario tags. By passing a string like @UITest into the hook annotation, we create a condition. As seen in this routing diagram, the setup gate swings open and executes the browser initialization solely for scenarios carrying the UI tag. The API test package is routed around it entirely. During runtime, the engine rapidly evaluates the metadata tags on each feature file. It maps those tags against the available hooks and only injects the matching setup logic into the execution timeline. By utilizing conditional execution, a rigid framework becomes highly targeted. As the framework scales, we encounter a final architectural challenge: managing multiple hooks that are configured to trigger at the exact same phase of execution. If a scenario requires both a database connection and a browser launch, the engine needs to know which @before hook to run first. We control this using the order parameter. Chronologically, multiple @before hooks execute in ascending numerical order. The engine processes order 0, then steps down to order 1. But the teardown phase relies on strict asymmetry. After hooks execute in reverse descending order. The engine processes order 1 first, finishing with order 0. This creates a last-in, first-out nested U-shape architecture. Setup logic physically closest to the scenario is the very first thing stripped away during teardown. Consider the practical dependency. If you configure order 0 to establish your database connection and order 1 to launch your browser, the application relies on the database being active while the UI is tested. When the test ends, you must close the browser at order 1 before you sever the database connection at order 0, or the application crashes. Stack ordering logic dictates exactly how the system is constructed and dismantled, preventing dependency collisions and ensuring safe teardowns at every layer. Even with strict chronological control, engineers often introduce architectural confusion by mismanaging where these prerequisites live. Cucumber provides another keyword called background. Placed inside the feature file, it also executes steps prior to a scenario. This presents a core framework design dilemma shown in this comparative matrix. When should a team utilize the visible background instead of hidden hooks? The design rule for the background is strict. It is reserved exclusively for common, domain-level steps that communicate direct business value. If the prerequisite is the user is logged into their account, that provides essential context to the product owner. It belongs in the background. Hooks operate on the opposite rule. They manage hidden system states. If the prerequisite is the Chrome WebDriver was initialized, the product owner does not care. It is a mechanical necessity, not a business requirement. It belongs in a hook. Blurring these responsibilities degrades the entire test suite. Writing database connection strings or browser instantiation checks into the feature file background destroys the readability and intent of the behavior-driven process. Professional framework design relies on maintaining this strict separation. Visible domain logic remains clearly formatted in the feature file. Invisible system mechanics remains securely managed in the hooks. As we step back, the value of this architecture becomes clear. Like the gears in this synchronized mechanism, the execution lifecycle operates in perfect sequence, preparing the macro environment, cycling through micro transitions, applying targeted conditions, and routing priorities. Mastering this lifecycle achieves 3 primary architectural benefits. It guarantees zero code duplication across test files. It enforces a clean separation of concerns between business logic and system code. And it provides highly scalable environment management. Moving past the basic syntax of test automation to truly command this hidden lifecycle is what elevates a practitioner from a simple script writer into a true framework architect.